All right, so let's continue with our third segment of this first workshop on Python. And as the slide shows here, we're going to be dealing first with overall program structure and also individual structure components. And then we're going to introduce the concept of separate functions, user-defined functions, and that will carry us through to the end of this segment. And then the final segment will deal with vector and matrix calculations in Python. So what we see here is sort of a standard layout of a typical program where we have a start and the end, and generally we specify some basic data, carry out some computations to obtain results, and then we display the results. So what we're going to do here is illustrate some program structures, and I'm going to pop over to the Spider Python interface, and I'm going to enter some code in the editor window, which will illustrate a couple of the initial and simplest structures, and those are if statements. And then we'll go back to a slide to summarize what we've seen. So I'm going to start by getting a value x from the user the way that we have done it before. And then I'm going to consider how would I square this value and preserve the sign of the value. Now, there are different ways of doing this, for instance, using a sign function, but I'm going to illustrate the use of if structures here. So I'm going to start out with a simple one where I'm just going to make a calculation. SGN x2 is equal to x squared. And then I'm going to have an if statement. If x is less than 0, colon, and you'll notice when I hit the enter key, it automatically comes down one line and forms an indent of 4 spaces. And the indent must be 4 spaces, and that's why it assigns that automatically. And then here I'm going to say SGNX2 is equal to minus SGNX2 to preserve the negative sign. All right? And then to finish off here, we will do a little print statement to display our result. And whoops, let's go back. Put that up here. And this is our simple code. So square the number, and if it's negative, the square is going to go positive. And then check to see if x is negative, and if so, reverse the sign of that square and then display it. So let's see what happens when we run this. It asks down in the console here for a value of x. So if I put in 4, it displays 16, which is what we'd expect. And then I can pop up an arrow here and run it again and put in -4, and the result is -16. So that is a simple one-way if structure, and there's an alternate structure to this for when you have, it's best used when you have something very simple like this, and that is to condense the if structure into one line. So let's do that. And this we would call a one-line if. And we've got a colon here, you notice, after the if x less than 0. And then we should be able to run that, and we get the, whoops, I don't want that there. I want it down in the console. Thank you very much. Minus 20, and the result is minus 400. So that gives us another way of doing that with a one-line if. And then we will illustrate this in a different way with a two-way if statement. And so I'm going to remove this calculation here, and then I'm going to say if x is less than 0, then the sine x2 is equal to minus x squared. And then I'm going to have an alternate, which is else colon, and I'm going to have SGN x2 is equal to just x squared. Now you'll notice that I don't have a terminating statement here, as you might expect to have in other languages like VBA or MATLAB. When Python recognizes the end of the indentation, that ends the structure. You notice it's displaying the keywords here in blue, and this is a two-way if, and I'm thinking if I'm able to run this and come down and put in minus 9, the result is minus 81. If I run it again and put in 9, the result, whoops. Whoops, I had a mistake here. That's why you check the alternatives. I had an extra sine x2 in there. So let's try that again. Let's put in 9 down here and expect to get 81, and we do. Okay? So that is that. Now let's go back to the slide and summarize these structures with a flowcharts and with the overall format and the example. So the flowchart up here shows the one-way if. It tests a condition. If that's true, it does something. If it's not true, it doesn't do anything and just continues. And here, in the two-way if, it tests a condition. If it's true, it does one set of computations. And if it's false, which is the else clause, it does another set of computations. So this is the first structure that we used with the one-way if with the true alternate on a separate line. And then we condense that into a one-line if here. And then for our two-way if, we used an if with a condition, and then we used an else. Another word that might be used there to describe it would be otherwise, but you don't use that in the code. And then we make the calculation without the minus sign. And we note here that there is no end statement to these structures. The structure is terminated when the indentation is removed. Okay, so let's go on from that and look at what we call the multi-alternative if statement. And it's shown here in a more complicated fashion. But essentially, the flowchart shows us testing a condition, and if it's true, we do a block of code and exit. And if it's false, we test a second condition, do a different block of code and exit, so forth and so on. All right. And then we have the final one where we do this and exit. And then if all of these tests are false, we can have a set of code that will execute, that is the else code. Doesn't have to be there, but it quite often is. So the syntax for this is similar but expanded from our two-way if, in that the intermediate tests, instead of using else, we use ELI if, and then our second condition with a colon, and our second statements, and so forth. And then finally, we use an else with the else statement. And you can see the indentation there. Okay? So we're going to show how to implement this with an example. that I will describe on a slide first, and then we will take a look at the code for it. I will load that in because it is fairly lengthy for me to type it from scratch right here in this workshop. So here's an example, and here we're looking at an instrument to measure temperature, which is called a thermocouple, and it has a particular type that's associated with it, and this one is called type J. We'll describe that in a minute. And essentially, a thermocouple gives us temperature versus voltage produced, and it involves the use of two metallic materials that form a junction where you're measuring a hot temperature, and then there's an alternate junction here going from B to A where you have what is called a reference junction or cold junction. And then the voltage here, which is usually a small voltage in millivolts, is proportional to the difference between the hot junction and the reference junction. And we could call that a DT. So if we wanted to know the actual temperature, we would need a separate measurement of this temperature to add in to DT to get the actual temperature. So thermocouples are the most common devices used for industrial temperature measurement, and the type J thermocouple is the most common thermocouple. Another very common one is called a type K. And the alloy materials or metal materials for one of the is iron, and the other is an alloy called constantan. And constantan is a copper-nickel alloy with those percentages. Now, it turns out when we want to describe this proportionality, it is not linear. It's sort of close to linear, but it's not. And also, it's very hard to describe with a single equation over the entire range of measurement of the thermocouple. So the National Institute of Standards and Technology, NIST, has developed a way of doing this where there are three different polynomials, and they're fairly high order, 8, 7, and 5, that describe the DT value, all right, given the voltage for different ranges of the voltage measured. And here it's in millivolts, -8 roughly up to 0, 0 to about 43, and 43 up to almost 70. And outside of these ranges, the thermocouple does not provide accurate measurements. So the overall range here is from -8.1 millivolts to 69.55 millivolts. So that is what we want to implement in Python code. So let's pop back over to our editor and let me go find a file here that I want to open. I have to do a little bit of chasing around to get there. And this particular one is called type J, TC. So I open that, and the first part of this should look fairly common to you, where I'm entering a value of the voltage measured in millivolts, and then I'm entering a value for the cold or reference junction temperature, and that would typically be measured with another device, or it would be a junction that is kept in a cabinet that is controlled to a given temperature. And then here is how we set this up. If the voltage is less than 0, we have the one polynomial. If it is less, and then if that's the case, it does this and exits the structure. If not, then if it's less than 42.919, which means that it's greater than 0, but less than that, the second polynomial comes into play. And if that's not the case, then the third polynomial comes into play. Now, we'll get back to the fact that we haven't checked for erroneous inputs here or out of range inputs, but we'll get to that. And then finally, the actual temperature is equal to the hot junction delta T plus the cold junction temperature, and we can print that out using this print statement, and you should be somewhat familiar with the use of this format specifier now, because we've been over that before. So that's what we have here. The other thing I will make note of is that these polynomials are really long-winded, so we put a continuation character in here, and because we're not dealing with something like a list of arguments in a function, the backslash continuation character is required here so that we can continue this on to subsequent lines. All right, so that's getting around to when you really need the backslash character. So if we run this guy, it's asking us for an EMF in millivolts. So if I put something like 35, then it wants to know the cold junction temperature, and let's say that's 20 Celsius, then it turns out that that indicates a temperature of about 632 degrees C. And the 35 would be using the middle polynomial here. If I run this program again and enter a value in something like minus 6 millivolts, again with a 20 degrees C, I end up with minus 135, and that's using the upper polynomial. And if I run it again and put in a value of like 55 millivolts and 20 degrees C, then it's 950 degrees C. So you can see that, just as an aside, this thermocouple measures a relatively wide range of temperatures, and if you start getting it too hot, then essentially the alloys decompose or melt. So that's what we have illustrating the multi-alternative if. We'll come back to it to make it a little more what might be called idiot-proof in a little bit here. So let's pop back over to our slide and show that that code is illustrated there. And there's one example that is shown over here on the right. And I make a comment at the bottom that this script does not protect adequately for erroneous user input or out of range input, and we will consider that later. Okay, so those are the if structures, or what might be called selection structures. And now we're going to go on and look at repetition or looping structures. And the idea that we have here in a very general sense is shown by the flowchart on the left, where we have an entry point and we have perhaps some computations that we carry out, not absolutely required, but commonly, and then we check to see if we are at a condition that allows us to get out of this loop. And if we are, then we exit. If not, we do what are called post-test computations and loop back and do it again. All right. So obviously something has to happen with these computations that eventually make this condition true. Otherwise, we'll never get out of this loop. So the syntax for this is a little bit awkward in Python, but it's similarly awkward in MATLAB because they do not provide a convenient structure for the general loop, whereas VBA in Excel does with its do loop structure. So here, the structure that we use is a while structure where we have while, condition, do the loop statements, and then do it again until the condition changes. That's the general structure, and what we do is that we rework this structure so that it can operate like our general loop flowchart over here. And what we do is we put in while true, Now, true is a constant, a Boolean constant, which says that true will always be true. And according to the while statement, we will never get out of this loop. But what we have is our pretest statements here, and then we test a condition, and if that condition is true, we execute the break command, and that gets out of the while loop, and it goes according to our flowchart. And if the condition is not true, then the post-test statements execute, and then we loop back again. And this is a similar adaptation that we use in MATLAB. The one comment we make here is there may be situations where either the pretest or the post-test statements are missing, depending on the situation, but they cannot both be missing, otherwise you'll never get out, all right? So that's what we've got there. So what we're going to do is we're going to take a look at that thermocouple program, and we're going to do a typical application of a while loop there, which is called input validation. So let's pop back over here, and let's get rid of this guy and do a file open. And it's making me go find it again. I'll try to fix that later on so it remembers where it was the last time. Okay, and okay, and okay, and okay. And come down to the bottom of my list here, GC with input validation. The lower part of this code is the same as it was before, but the upper code has a while loop, and you see it has while true. And then the pretest code is that we get a value of voltage from the user, and then we check it against the limits of our correlation, noting that it has to be greater than or equal to minus 8.1, and it has to be less than or equal to 69.55. If that is the case, we execute the break command, and the execution comes down here. If that's not the case, it means we're out of range, so we print a corrective message to our user, and we come back and repeat the loop and ask the question again. All right, so this is a very typical example of a while loop. Input validation is not the only thing that we run into for while loops. We'll see other examples in the following workshops, but for now, we can use this as a good example. So if I execute this, it wants me to enter the millivolts. And so if I put in minus 10, it says the voltage is out of range, please re-enter. And then if I put in minus 8, it likes that, and I can put in my cold junction temperature, and it gives me that. Now, if I run that program again, and I enter something which is 70 millivolts, it says that's out of range, please re-enter. So if I enter 69, it's happy, and put in 20 again, and we get a little more than 1200 degrees C. So this shows that for you, and you have that file available to you. And let's pop back over on the slide and take a look at it. The code is over here on the left, and this is the input validation structure. Acquire an input value, check whether it's valid or not, and if it is, break. Otherwise, print a corrective message and come back and ask for the value again. And this shows some examples and the name of the file that contains this particular script. Okay? So that's what we're dealing with the general loop. And now we're going to look at a couple of variations on that, which are called list-driven and count-controlled loops. And so let's move on a slide. And this shows two different flowcharts. The list-driven loop, which is somewhat particular to Python, is that we have a list of items and we come and we check, are there items left in the list that we have not processed? And if the case is yes, then we select the next item in the list, do loop computations, and come back around, and eventually we will have selected all the items in the list and we exit. So that is a list-driven loop. And then a special case of this is the count-controlled loop or for loop, which you may be familiar with from other programming languages like VBA or MATLAB. And here we have a count variable that has a start, and then we check whether it is greater than or equal to our end criterion, and if it is, we're done. Otherwise, we do loop computations, and then we add a step to the count variable, and then we continue doing this until finally it has reached its end. So that is the count-controlled loop or for loop. And now what we want to do is we want to illustrate some applications of that. So we'll do a simple one by typing it in, and then we'll look at some other examples where I load in the code. So let's come back over to our editor. And let me get rid of this. And I'm just going to come back and select all of that and delete it, and we'll make our code here. So what I'm going to do is start with import numpy as np, as we have done many times. And then I'm going to do a loop for x in, and I'm going to give it a list. And the list is going to be 30, 45, 75, and 125. So for the items in those lists, sort of taken one at a time, what I want you to do is calculate y, all right, which is equal to the cosine of, now the items in the list are degrees, so for the cosine function I need them in radians, so I can convert that a couple different ways. An easy way is to borrow the radians function from numpy and then put x in there, like so, and that gives me the value of y. And then within that loop I can, print. And I'll just take a specific format here in the braces, and that would be first format 0, and I'll make it 5.2f for floating point, and then I'll do dot format y. So I'm just going to print out each one of these when I do it, okay? So that's a general list-directed loop, list-driven loop. And so let's see what happens when I run this. And down here, you'll notice that we get the values of the cosine function for 30, 45, 75, and 125 degrees, all right? So the list, since it is a list, it is quite flexible. You could have text items in there and your code could do something with the text items, but that is a simple, general list-driven loop. Now, when we expand that to something more like a count-controlled loop, we make use of a special type in Python, which is called the range type. So let's go over and discuss that on a slide, and then we will show you how it works, okay? So let's come over here and look. So the first example up here is what we just showed you for variable in list and then loop statements. And you'll notice, as usual, within the structure, they are indented. Now, the use of a range type is very common in order to generate a numeric list. And that statement is range, start, and step. All right? And it just notes here, if we leave the start out, it assumes the value of 0. And if we leave the step out, it assumes the value of 1. All right? So it shows an example here of what happens if you actually assign the range type result to a value X and then print that value in the form of a list. And this just shows you what happens. You don't often do this, but it's sort of to reveal what happens. And that is that if we go 0 to 12 in steps of 3, you would think about that as 0, 3, 6, 9, 12. But as happens with some other functions like the arange function in NumPy, the last item is left out. So you get up to, but not including the last item that's generated by range. So you get 0, 3, 6, 9. All right? Now, here are some examples over here on the right. If I just do range 10, that means it's starting at 0, and it's going to go up to 9 in steps of 1. So you get a list of 0 to 9. If I do generally range n, where n is an integer variable, it's going to give you a list from 0 to n minus 1. If I do 1 to 11, it's going to start at 1 now, but it's going to end at 10 because the step is 1, and it's not going to give you the last item. And here's another example. If I go 0 to 11 in 3, all right, it's going to be 0, 3, 6, 9 again, because when it goes to the last one, all right, that it's going to leave out, and that is actually greater than 11 because it's 12. So those are examples of the use of that. And so now what we're going to do is we're going to come back over and look at a couple of examples that illustrate the use of the for loop with the range type. So let's come back over to our editor, and let me save this file, and that will give us something that it will remember, I think. So bear with me a second. Okay, and that one was just an illustration. Simple list loop. So we'll do that. And then what we can do is open a file. And this file is going to be called for loop example. And it looks like this. So let's take a look at the code that we have. First, we've got our NumPy import, and then we create an array of X values, 6 of them, shown here. We know how to do that. And then we use the len functions to count the number of items in the array. The len function doesn't require NP. It is inherent to Python itself. And then what we do is we set a variable sumpos, sum of positive numbers equal to 0, and then we say for I in range n. So when we say for I in range n, range n is going to generate a list of values from 0 to n minus 1. So it's going to, in terms of indices up here, 0, 1, 2, 3, 4, 5, because we have 6 items. And then it says if X, essentially index I, that would correspond to each one of these values, is greater than 0, then add that number to this sumpos variable. If it is less than 0, don't add it, all right? So this shows a simple use of a for loop where we have a variable and we use an index of the for loop as a subscript or array index. And then it prints out the result when we're done. And if we do this, we get 12.2 because it added 2.3 and 1.5 and 8.4, and it ignored the negative elements. So that we have there. And then we're going to show you another example which uses a two-dimensional array, all right? And this is taking a step further with a for loop within a for loop. So this one is called nested for loops. So let's open that. Okay. So here, and we've shown an example of this before, where we create an array which is two-dimensional by providing three lists, which are essentially the rows of the array. And it's a 3 by 3 array. And then we start the same way with sum of squares here, all right? And then what I do is I say for I in range 3. Now range 3 is going to generate the value 0, 1, 2. And for j in range 3, again, the value 0, 1, 2 in the list. And then it's going to, for I equals 0, it's going to process j 0, 1, 2, and it's going to add the sum of the squares of those values in our two-dimensional array. And then when it's done, it actually takes the square root of the sum of squares and indicates that in its result. So it's a little different than the example before, but it shows you how to put one for loop inside another. And this comes up quite frequently when we start dealing with matrices. Okay, so if we run that, we get a result of 19.6. So that we have, and if we go back to the slides, you can see that we illustrate that here and provide a little explanatory text out to the right, essentially what we just described to you, okay? So the next thing that we're going to illustrate is the use within a loop of the break command. And we already illustrated that with the general while loop, but we can also use it in a for loop. But let's illustrate it with another set of code in a while loop. So coming back over here, let's get rid of a couple of these, and let's open something called Sentinel Break. Okay, so here we're illustrating a couple of new features. The first thing is we create an empty array. You notice it's an empty list. So it's an empty array. And then we have our while true, which we described before, and we get a value from the user, and we check whether this value is minus 9999 or not. That is called a sentinel value, and it's an entry from the user that says I'm done. So if it is minus 999, and you'll notice here when we do this test, if data in, we're doing a logical equals test, so we use a double equal sign. If data n is equal to minus 9999, then break. What break means is get out of the while loop. Otherwise, if it's not the case, we append the new value, data in, to the previous test data array, all right? So let's see how that works. Come down here, and I'll just enter the value 1. Now it wants another value, minus 3, and another value, 45, and then eventually I do minus 9999 and enter, and it's done, and it shows the array that it produced was 1, minus 3, and 45. It did not include the minus 9999 value because that was our sentinel, and we broke out of the loop before we appended it to the array. So that shows you the use of the append function within NumPy, and starting with an empty array and using the break statement to get out of a while loop like that. So coming back to our slides, again, this indicates that and shows a different set of examples, but works in the exact same way. All right. So the next thing that we're going to do is show the use of a different statement within, in this case, a loop, a for loop, which is called the continue statement. So let's come back over to our editor and let us open a file which is called random continue, down here somewhere. There it is. So here we're bringing in another module. In this case, it's not NumPy. It's the random module, which gives us the opportunity to generate random numbers. So that's a new illustration for you. And then we're going to make a plot, so we bring in the matplotlib pyplot submodule. Start with an empty array, just as we did before. And here we say for I in range 1000. Now, again, remembering what range does, that's going to create a list starting with 0, and it's going to go up to 999. And it will not include the value 1000. But since it includes 0, it contains 1000 numbers in the list. And then what the loop does is it says we're getting a random number from the normal distribution with mean 0 and standard deviation 1. That's how that works, all right? And you can get some information on that from help over here. And then it says, if the random number is negative, continue. Now the difference here is it's not break out of the loop. What it says is, if the random number is negative, continue the loop, but don't do any more statements before you do that. So what that says is that we'll only append this random variable to the test data array if the random variable is greater than or equal to 0. So this shows the use of a continue statement, which is don't do the rest of the statements, just go back and do the loop again. And then finally here, we do a quick and dirty histogram of the data with 20 bins or intervals just to see what it looks like. So let's come over to plots here and let's run this. And this shows the fact that we've got what looks sort of like the positive half of a normal distribution because we neglected to include any values which are negative. And that's what the continue statement does for us. So let's go back and look at the slide for that. And there's your code, and there's some explanatory text below. Then you can see the result over to the right. And for the first time in our workshop here, we're making use of the random module, all right, for random numbers. Okay? So that completes our sort of rapid discussion of the general program structures in Python for selection or decisions, if type statements, and for repetition structures or looping type statements. And so we're going to move on now, and we're going to get into the latter part of this segment of the workshop, and that has to do with getting involved with user-defined functions, which is up here in the title. So the idea of a user-defined function is shown in the flowchart in the upper left here, where we have a function that is defined, and we use the DEF abbreviation to define the function. We give it a name, and this syntax is somewhat different than you find in like MATLAB. And then we have possible input arguments for the function, and the function returns an output when it encounters a return statement. All right. So if we go back to our initial illustration here of squaring something and retaining the sign, this shows here what a function might look like that would do that. And it starts with an argument x, and then within the function it squares it. It checks, as we did before, to see whether it's negative, and if so, it reverses the sign, and then it returns that value. If we didn't have the return statement, this function would execute, but you would not get any result. So here we have tried a couple of tests using SGN SQR of -2, and we get -4, and of 2, and we get 4. All right. So we can expand this a little bit, as shown over here on the right. And actually, if we want, we can store this function. We don't often do this for something that simple. We can store this function in a separate Python file with an extension .py, and then we can, this Python file is called _function, and then from that file we import this function, and then we can use it in our code. So that happens more frequently when you have a function which is much more extensive and you want to store it in a separate file. But the general code syntax is DEF, the name of the function, an argument list, and then you have statements, and then you have the return statement to return results, and that's what that looks like. Okay? Now, there is a way, just like when we had the one-way if statement, then we could make it into a one-line statement. There is a way to abbreviate the def description of a function in something called a lambda function, and we'll illustrate that here on the next slide. So here we have a function that is shown in 2 lines, get y with a value of x and slope a, intercept b, and we return a times x to the b. Sorry, it's not an intercept, it's an exponent. All right, and so you'll notice here that instead of returning a variable, we can actually make a computation and return that in the same line. So another way of doing this is we can define the function in a single line with the use of the word lambda. It's a little bit similar to using an anonymous function in MATLAB, not quite the same. And what we say here is that the lambda function has arguments x, a, and b, and the rule, or what it computes, is ax to the b. So when we define it this way, we can set a equal to 4, b equal to this, and then print get y of x equals 0.5 and the values of a and b, and it gives us the answer. So it's just a neat way to have a function on a single line. Now, we can also write the function without including the A and B arguments. And then if we do that, we absolutely have to provide these A and B arguments in our script. Some of this gets to the concept of scope that we're going to be talking about momentarily here. Then I can just say print get Y, and it gives me the same answer. Okay? So there are other examples. Let's go back and take a look at several examples using our Spider editor. So the first one I want to look at here, let's open a file which is called function with no arguments. So let's see if we can find that. Okay, here I have defined a function, and the idea here is if we include the function in our script and then we're going to use it, the code for the function has to precede the point where it's used. All right? Now that you may not have run into that before in other languages, but that is the case here. And if the function were stored in a separate file, you would have had to have the import statement before it's used. So here we've got a function called halfRand, and it doesn't have any arguments because it doesn't need any. And so what it does is it has the same while loop that we had before, and it returns this random number, which is just a random number that is the first one that's positive, all right? Because if it got negatives, it would break out of the while loop and repeat it, all right? So if we run this, we see that we get 0.388, and if we run it again, we get something a little bit different, okay? 2.049. So this just illustrates that we can have functions that have no arguments at all right? And then we can say, well, we can have a function that has multiple arguments. So let's open up a file that illustrates that. And this is similar to what we had before, but here we have two arguments for the function, mu and sig, which represents the mean and the standard deviation of our normal distribution. And what we now have is, instead of 0 and 1 here, we have these arguments specifying what distribution we're using. And then we're saying we only want the random numbers that are greater than the mean, mu, and otherwise break. And so here is a test where mu is 100 and sigma is 20. So if we run that, we get a value of 110.943. And if we run it again, we get 115.62. And they'll all be positive every time we run it. So here's a function that has two arguments in it. So let's pop back over to the slide and review that. This shows the function with no arguments and then shows the function with two arguments. And that's to give us the flexibility of changing this from 0 to 1 to whatever we want by using these arguments here. Okay, so that is that. And now we're going to look at a variation on this, which is important to be aware of, and it's called keyword arguments. And so let's open that. And here, what we've done is we have the mu and sigma arguments here, but we have given them default values of 0 and 1. that means that if the half-rand function is called without any arguments, it will use 0 and 1 by default, but it can use different arguments if we specify them. And as shown down here, we're specifying sig with a value of 0.1 instead of 1, but we do not specify mu, so it's going to adopt the default value equals to 0. All right. So if I run this function, it gives me values which are much smaller because the standard deviation is equal to 0.1 instead of 1. So this shows the use of keyword arguments, and it turns out that since they are keyword and you have to specify them in this way when you call the function, you can actually put them in different order. They don't have to be in this order. In other words, I believe I could put in here mu equals 10, 10, like so, and run that, and it gives me the answer. And the order here is reversed to the order in the function definition, but it doesn't care because I have identified the appropriate argument names that I have, and these are keyword argument names. Okay? So, popping back to our slides, there we go, and you can see essentially what we've illustrated here. And the only thing I added a specification of mu down here to show you that they didn't have to be in that order, and it mentions that here. And the default value is used for any argument that is left out. So that is the use of a keyword argument. And you'd say, well, when would I want to use that? Well, you might want to use it when there are default values that somebody using the function would just like to accept. All right. So we have that. All right. And so let's show a couple of examples of using functions. And we are going to deal with calculating percentiles of an array. So let us come back to our editor here and put a couple of these guys away, and let's open a file called percentile1. All right. So what we're dealing with here is we want to provide a value of a percentile of an array of values. So for in our example down below here, you can see we have a set of values 2, 4, 6, 8, 10, and they range from 0.1 to 6.7. So we might want to say, as we say here, what value estimates the 25th percentile of this array, all right? And if we run that, it says it's essentially 1.1, all right? And the way that it makes that calculation is a standard way of percentile calculation. It's available, for instance, in Excel with the percentile.exc function, where we calculate the length of the array, and then we calculate a value in the array for our percentile times n minus 1, that is an index then, and a value that is the integer part of that, all right? So we truncate off any fraction. And then we do a proportion of the value to the truncated value times the 1 value, and then 1 minus that times the next value in the array. So that's how that works. So if I come down here and say I would prefer to have the 60th percentile, and run that, it gives me 2.78, which is somewhere up in here. Now, the one requirement that we have for this calculation with this function with two arguments is that the array has to be in ascending order, smallest to largest value. So let's take a look at an improvement to that, which is the file called percentile2, I think. And the only thing that we've added here is that we have brought in NumPy, and then we use the sort function in NumPy to sort the X array into a sorted ascending order Y array, and then we do the same calculation but with respect to Y and not X. And you'll notice our numbers here are similar, but they're mixed up in terms of order, so that when I run this, I still get the 1.1 result that I got before. Okay? So let's come back to our slides and just document what we've done there. It shows the first one with the sorted array, and then it shows the second one where the array is not sorted, but we invoke the sort function in NumPy to get it sorted. All right? And then you may need to look through this code to understand again how it is coming up with the percentile value, but I think you can sort of see that it's taking part of the MP1 value, this int, and then it's taking the complementary part of the MP, the next value in the array. All right, so that is how that is working. Okay, so let's move on here and talk a little bit about expanding our ability to work with functions. And the next thing we'll talk about is how you can invoke one function within another. So essentially embedded functions. So let's come back here and take a look at a function called IQR, which relates to the percentile function. IQR corresponds to interquartile range. I don't know if you remember that from your statistics course, but the IQR is used, for instance, to develop a box plot. And so what we have first is our standard percentile function that we just illustrated, where you sort the array. And of course, if the array is already sorted, the result of the sort is the same array. And then we have an IQR function that uses X, and it calls the percentile function within the IQR function, and it gets the 25th percentile and the 75th percentile and takes the difference, 75 to 25, and that is called the interquartile range, or the IQR. So for the result that we had before, if we run that, we see the IQR is 2.4. So this shows you how you can invoke one function within another, all right? And that's a good illustration there. And then the next thing that we want to take a look at is what happens when the argument to a function is actually the name of a function. And that, if you remember from MATLAB, you end up using an @ symbol for that, and it turns out to be much easier or direct in Python. So let's take a look at that and come back to our editor and pop out these percentile calculations and open a file that is called function. File, open. Function. Okay. So what we're doing here is, what we're saying is we got an array that contains values of X, and we want to plug them into an as yet undefined function and essentially get values of y, and then we want to return the average of those values of y. So we're plugging x into a formula, getting y results, and computing the average of those. But what we've said here is that we're specifying the function that computes y as an argument to this function funavg. So we use a generic name func here and down here to make the calculations. And you'll notice essentially what we do here is we find the length of x, and then something you'll see again coming on in the next portion is we use a function in NumPy to generate an array that's just filled with zeros and has a length of n. All right. Now remember, the indices of that array will be 0 to n minus 1, but its actual length is n. And then we say for I in range n, which means 0 to n minus 1, calculate the y values by plugging the x values into func, whatever it is. And then finally down here, from NumPy, we use the mean function, which is like the average function in Excel, to compute the arithmetic average of the y values, and that's what is returned. So below here, we use a lambda function to define f, and all that it is a cubic equation in x, and then we create a set of 50 values of x from minus 10 to plus 10. Remember, with linspace, the default number of values is 50. And then we say that we want the average of these x values plugged into this formula. So for our fun average now, we supply f, which is the name of this function, and the x values, and it's supposed to print out the average value. And that's what the average value is, down there, about minus 27. So again, moving forward with our slides, that's what this was the IQR, and this is what we have here. And so the first argument is sometimes called a dummy argument because it's not defined until it's supplied by the call of the function. And the second argument is an array of values, and then we're computing the average of the whatever supplied as the function and x plugged into it. And then this defines the lambda, what the lambda function is, and it shows the result down at the bottom. Okay? So that shows that. And then what we're going to illustrate next are a couple of specialized features of the use of these functions. And that is when the functions have an undefined set of arguments. So let's come back to our editor and open a function. It's called with pass-through. And you'll notice a little difference here in the personality, because what we say is that this function, whatever it is, has to accept this array of x. But we also say that this function may have other arguments, and we're not saying what they are. All right? And then when we invoke the function down here, we include this general list of other arguments in invoking the function to get our answers. So here, now for our lambda function, we have x, but we have 4 additional arguments, which are the coefficients of the cubic equation. And then for an example, we define values for a, b, c, and d. Same statement to generate the x values, but now we invoke funavg with the name of the function, and x, as we did before, but also the additional arguments A, B, C, D. Now, those are covered by the asterisk args word up there, and then A, B, C, D are passed through here when we evaluate func, which is actually means F, all right? So if we run that, we get the same result. But now, for instance, I could change one of these values here to like plus, and we would get a different result, okay? So this shows that what are called pass-through arguments, and that you may have run into that in MATLAB, for instance, when you call MATLAB routines that where you need to pass arguments through the MATLAB routine to a function that you create. That's an example of that. And so, again, coming back to our slide to document that, this shows the use of the asterisk ARGS, and then how it's used within the function definition, and then when the function is called within the function, fun average, all right? And, we wouldn't have to use a lambda function here. We could use just a general DEF of F, but I've used the lambda function because it's more compact, okay? And the only curveball on this is, what do we do when one or more of our arguments is not a generic argument, but is a keyword argument? So let's show an example of how you handle that. So function with pass-through keywords. Here we go. Now, you'll notice immediately that the difference here is instead of using ARGS, we've got KW standing for keyword args, and we have double asterisk and not a single asterisk as we had with args. But apart from that, it looks the same here. But then when we come down and we define a function here, it's what we had before, but now it has these keyword arguments, mu and sigma, all right? And so that's where the difference is. And then this is our generate random number, all right? And in this case, we've got x being values from 1, you might think, to 1001, but remember that A range leaves out the last item. So it generates values of 1 to 1000. And then we get a norm average by supplying genrand as our function. And then x as our array. And then here we only modify sigma, which means the mu will stay at 0. And it will pass that through as a keyword argument, all right, when we call it. So I think this will work. Let's see. Yeah, and it comes out with 3.32, all right, which is a result that it gets. And since they're random numbers, if we run it again, we'll get a slightly different number. So that's the way that we can handle keyword arguments. And you might say, well, what if we have both? What if we have generic arguments in addition to like X, and then we have keyword arguments? And you can do that, and it's typically handled by having the asterisk ARGS first, and then comma, double asterisk KW ARGS as second, all right? That's the typical way that it is handled. And like with keyword arguments, you can supply them in any order. We don't really like to mix those up with our regular arguments, so we usually put them last, all right? So let's come back over to our slides and take a look at this. This is what we illustrated to you, and you identify it with double asterisk KWARGS, and you include keyword arguments with default values when you define the function that's going to be passed into FUN AVG. Here we illustrate only specifying the sig value, and the mu value will retain its default value of 0, all right? And we give the file that illustrates this, okay? So that may hit you with a bit of complexity, but I think after you see a number of examples as we go through the Python workshops, you will become more comfortable with it. At least I hope so. So to finish up our discussion in this third segment of our first workshop on Python, we're going to consider the concept of variable scope. All right, so let's take a look. This just summarizes what we've said about arguments. So we'll leave that at that and talk about variable scope. So what we mean by variable scope is where can a value be seen, all right, in your script. So in this first example here, what you see is within a function, which is sort of a nuisance function, it just does something for us, of x, we define a and b, and then we return a value of ax to the b power. And then we run the function here, or try to run it, and then we try to print or display the values of a and b, and we get an immediate error. It doesn't even let us run the function because it says, as far as it can tell, a and b have not been defined. And the reason they haven't been defined is that they're defined within the function, and the main script cannot see into the function, all right? Cannot see into the function. So if instead we put the print statement within the function, then it has no problem displaying the values of a and b because it can see those values within the function, all right? So that is the concept of scope very simply, and that is that values within functions cannot be seen from outside the functions, all right? And in fact, it won't even let you go there. It actually gives you the red dot errors before it'll run it. And the other comment we make over here on the right is that arguments to functions, such as x up here, all right, that those are called formal parameters, and they are not local variables. I apologize for the phone ringing here. It will stop in a moment. Formal parameters are sometimes called dummy arguments, and they are not local variables. They revert to the values and variables from where the function is invoked. So for instance, x here actually, when it's run, is the value 12.3, and it's not a local variable. And I just want to point out that distinction for you. So moving on, we change the game a little bit here, and we define a and b outside the function, and then we try to print it inside the function, all right? And it turns out that you can do that, all right, because the function has the ability to see variables in the main script, all right? It can see out, but we can't see in. So values in the main script have what is called global scope, and so we can refer to them inside the function, all right? And here, if we run this function, it displays the values and displays the answer down here. And then, just as in MATLAB, we can override this by the use of the global declaration within a function, where we have A and B defined within the function, but we want them to be made available outside the function or to be able to be seen outside the function, so we declare them as being global, all right? So that is a little bit in terms of scope. And the main thing to realize there is that the main script cannot see into a function, but from within the function, you can see variables in the main script. It's not quite a two-way street there, all right? So that completes this particular segment. It's been quite a bit for you, but we're going to take our break, and then we're going to come back and do the last part of the first Python workshop, which is going to deal with array and matrix operations. That's it for now. Let's take a break.